Hello, my name is Zoe. And my name is Professor Honey. And together we will teach you all about trees. Now, before we get started, please make sure to give this video a big thumbs up. Thank you so much. Trees, I love trees. Me too, they're great for the environment. And oh, they're the home to cute little baby koalas. That's cool, but I'm talking about the coating trees, you know? Wait, what? Let me explain. Let's start from the basic tree definition. Forest trees are now coating trees? That just sounds like gibberish. So trees are basically a bunch of nodes, which are like these numbers with a circle around them, connected to each other by edges, which are like these line/stick things that we can see connecting to each node. And they start from a root node, which is basically the topmost node, or the node that has no more parents. And the rest of them are considered children nodes. You can think of this like a family tree. However, the tiny tweak is that each parent can have as many children, but each child may only have one parent. Now, how do we really use trees? We barely use them, right? Nope, they're actually very important. So here are just two ways to traverse the trees: DFS and BFS. We're using these two algorithms to traverse the tree, which is basically like go through every single node inside of the tree. So DFS basically stands for depth first search. It traverses the tree column by column, and we can use stacks for that recursion. And BFS stands for breadth first search. It traverses the tree layer by layer, or you can say row by row, and we can use queues for the tracking. So if you're a visual learner, this one's for you. So this is how to visualize it. DFS, we can go column by column, like so. And like you can see, none of them really are overlapping. Why is that? Because trees, vertically, they don't have any nodes overlapping. And that is because no edges or two nodes are connected to each other by an edge. Vertically, like I say. So there's nothing like, if you continue this tree, it's not like there's a node over here, and connecting this, because otherwise this would be in line with the first root node, but that's not how it works. And now for BFS, which is basically the exact opposite of DFS. It goes this way, or layer by layer, row by row. And like you can see, they actually do overlap because they're in the same level, and trees do have levels. Now, I hope that made sense. Now we're going to talk about the implementation. Implement what? It basically means coding. So here's a simple template to print out the tree's value. And here we're going to explain it in detail. Over here, first two lines are basically calling the library. Yes, coding has libraries. And the next one is a struct, which is basically the value. It's basically like a big data structure with tiny data structures into it. And then you can use this big data structure to call another data structure. And this array, like you can see, can call anything inside of the struct. And now basically we have the traversal function. It has A as a parameter, and then we can first output the tree's value, then inside of for loop with the children's size as the limit, we're going to traverse the tree over and over again. That's basically the template. And now we're going to go do some exercises. But don't worry, with the template, it should be a piece of cake. So first we're going to find the depth. Now, over here, we can see something is different, right? There's a new attribute inside of the struct. And that's just part of it. Now, with this new attribute, we have to find the size somehow inside this traversal function, right? This is how to find it. So we're going to find the children's depth is equal to the tree's depth plus 1. Now, the tricky question is that where do we put it? We even know how to do it, but where do we put it? So we're going to put this right after the tree's value, because if we find the tree's value, we can find the depth with that information. And now that's just rather simple, right? We're going to do something a teeny bit more challenging. We're going to try to find the size. So over here, like you can see from the previous problem, there's another attribute inside of the struct, which is basically like replacing the depth is the size. So this is how to find the size. Now this funky looking plus equal sign is basically meaning, for example, if A plus equals B, you can turn that into A equals to A plus B, right? And then after that, that's basically what this plus equals sign means, which is basically a simplified version of this. And inside over here is another tricky question. Where do we put it? Okay, so do we put it here or do we put it here? Well, I'll let you pause the video and think about it for some time. Okay, well, now for the final time, the truth of it. I have this my eraser tool, and now which one should I erase? I'm going to erase this one. Well, if you chose this one, congratulations, you are correct. And now why is that? Is it just because, well, I don't like that arrow, I like this arrow? Well, no, it's because after you traverse the tree and you can find every single element inside of it, then you can find the size. You can't find the size with just the value. And well, that's exercise. Pretty simple, right? Now, what can we get from this? That order matters. Well, that's it. The coding world is full of so many amazements, and trees are just a part of them. However, in my opinion, they're the best. Well, thank you so much for watching. And again, please make sure to give this video a big thumbs up and vote for Zooey. Bye. Peace out.